Welcome to Unit 2 of the module. In this unit, we're going to examine early neural network models. These are ones which have their origins in McCullough and Pitt's work from the 1940s, and they were developed in the 50s and 60s among a diverse group of researchers pursuing different aims. And collectively, they constitute the first wave of connectionist research. Just as a little refresher, we had just introduced the very idea of a neural network, specifically a feed-forward neural network, in which we provide numbers at the input layer, and that leads to calculation of values at the hidden layer, which leads to calculation of values at the output layer, which we read off. The network just does sums that change based on the input pattern and the weights in the network. In a typical training task for a given network, let's say this one, we will have a data set in which we might have very many patterns and associated with them very many desired outputs. So we have, in this framework, we're considering a case where the researcher wants the network to learn to produce specific outputs given specific inputs. So the researcher has an idea of what the correct structure of a domain is. Let's take a very small example. On the left, we have an input data set consisting of 5 patterns. On the right, we have 5 output patterns. So the network needs to find weights which will generate the correct outputs given these inputs. We need to consider the input and output data sets as a whole, as well as considering individual patterns. So looking at these patterns, both inputs and outputs, we know nothing of where these numbers came from. They have no semantic attachments. They are merely numbers. The outputs, as we can see, are either 1 or 0. So one might look at this and say, what's the researcher doing? I see they're trying to interpret the computations done by the network as a form of classification. If we view this as classification, then we come to view the input data patterns as being tokens or representatives of specific classes, and the output value associated with them will be 1 if they belong to a specific class and will be 0 if they don't. Notice the complete absence of meaning here. All meaning is supplied by us. Now, we can uncontrovertibly train networks to do this kind of task, and we will be developing procedures for doing that. You'll be learning that. Our focus in this module is always going to be not so much on the computations which we have dealt with. We know what the sums are. But it will be, how do you interpret what the network is doing? So I'm going to give you 2 possible sources for these data. Supposing, for example, the inputs came from readings of 2 sensors of chemicals, and the output was a decision as to whether the resulting mixture or the chemical so measured was suitable for consumption. If we have a good data set, we could employ a neural network to do this if we have clear views on what is and is not suitable for consumption. In this case, the network might be employed to screen various mixtures and provide information that will allow the researcher to guide people's activity and say whether they should consume something or not. The exact same numbers could have come from a different domain. They might, for example, in the input, be estimates of the likability and trustworthiness of politicians, as obtained through questionnaires, polls, guesswork. And the output of the network, which is 1 or 0, might be taken as an estimate of whether one should or should not vote for the politician. You can see that these are two very, very different domains, and you can see that the employment of a neural network in either domain will have consequences. And most importantly, the network knows nothing at all about the domain. The network knows nothing. The network is merely doing sums. So, with that in mind, we need to address a little bit more detail about the computations that are done by these simple units in the network. Around the mid-1980s, neural network research, which had fallen into the doldrums, was resuscitated because of the development of powerful means for learning the required function, that is, finding the correct weights that will map from those inputs to those outputs. We will address later the question of how to find those weights. What's important for us to know is what's the business? What are people actually doing here? What they're doing is trying to develop weights within a network such that the desired mapping is computed. Now, we've got this far. We have units which have activation functions, and the logistic activation function shown on the right there will be the activation function of reference for us. When we look at the function computed by a unit with an activation function of this kind, we see that if its net inputs over the whole data set now were all below 0.5, this unit would always produce an output very close to 0. Likewise, if the net input of this unit taken over the set as a whole were on average larger than 0.5, then typically this unit is only going to produce an output of 1. Sensitive variation of the output of this unit only happens when the net input to the unit is somewhere within the range roughly of minus 0.5 to 0.5. Now, assuming we have very many input-output pairs, in our toy example we only had 5, but typically we might have hundreds, thousands, hundreds of thousands, millions. If we have very many input-output pairs, ideally our unit is going to be doing some work for us in the network. And so we would like it to respond sensitively to the variability that exists in the input set. If the input set as a whole is such that the net input to a given unit is approximately 0, then the unit will respond differently to different patterns in the input set, and the unit is doing good work for us. If, however, over the whole input set, the net input were clustered at a large negative value or a large positive value, then the unit will produce essentially the same output for all input patterns, and so it won't be contributing anything useful to the overall computation done by the network. To address this issue, we augment our simple computational unit, the Warren McCullough Walter Pitts unit that we have looked at so far, and we introduce one additional term which we add to its net input. And this term is chosen so as to shift the average net input of the unit to center it more or less about 0. So the situation is illustrated here with two units. The one on the left has an average input about 0 between the two red lines there. And so this unit is doing good work. We have a bad unit as well we have to worry about. The unit on the right-hand side is producing 0 for pretty much all inputs because the net input to this unit is centered at a low value. There's an obvious way to fix this, and that is to add a simple constant term to every input that will serve to shift the net input to the unit up or down so that it is centered around 0. This additional term in the computation of the net input is called a bias term. So we've added one more thing to this very simple computation of the net input to a unit. We have exactly the terms before, and we've added an additional term called the bias. Now our equation is just a little bit more complicated. However, there's a very easy way to implement this using the kind of formal structures that we've already considered. If each network unit had an additional input from a hypothetical unit that displayed a constant activation of 1, then the contribution to the net input of this addition will be a constant term given by the weight added to all computation of net input. And so a constant term can serve to shift the average value of the net input to the positive or negative end as required in order to center the average net input around 0. This is just an implementation detail, the manner in which we implement this. The fundamental idea is that the net input has an additional term, a constant value, such that the average net input will be 0. Implementing this using an additional bias unit with a constant activation of 1 is simply a way of treating the bias as if it were a weight in a network, and that becomes completely consistent and continuous with the way we will develop procedures for training networks, finding weights, and in this way then finding biases becomes just finding another weight. Now this bias term is only required for hidden units and output units. Remember, the values at the input units are ones we provide. We extract them by some procedure from the world. We code them as numbers and we present the numbers. Computation properly only begins with the hidden units and with the output units. The addition of this bias unit is so conventional that we rarely show it or mention it in our network diagrams and figures. In the pedagogical software system we will be using in labs, however, we will always show the bias explicitly because we want to keep the basic computational machinery of the networks in mind. Later on in lab, you can experiment with including or excluding the bias unit so that you can verify for yourself that it simply helps to have this additional term in the computation of the net input to each unit in order to ensure that the unit is contributing to the overall computation, desired computation of the network.